Good evening. Welcome to the week 3 of the live interactive session of the fabrication techniques for MEMS-based sensors, clinical perspective. I am Vikas Pandey, the PMRF teaching assistant for this course, and happy Independence Day to all. Okay, there's something about me. Mhm. For details, you can go to my portfolio. There's the meeting link and the YouTube link, as well as you can write on the email. Okay. So before moving into any questions, in the last class, we said that we will be seeing clean room standards, like what are they? Okay. And even before this, if you have some questions, you can ask. Hello.
No, sir, no
Okay.
doubts.
Okay. So in general, there are two type of clean rooms, two standards of clean room. ISO, one is the international standard, and Fed STD, that is US standard. It is still used very commonly. Like whenever we talk about class 1, class 10, they are actually US Fed standards. Okay, but there are equivalent ISO standards. They are mainly based on facts like you see in ISO 1, if you check, it is actually ISO is more stringent, you can say, more stringent. So it is based on zero point 0.1 micrometer particle size. Okay, so the maximum number of allowed particle size, if it is 10, that is 10 to the power 1, it will be ISO 1. If it is 100, it is ISO 2. If it is 1000, ISO 3, like that. And equivalently, we have class 1, class 10, and this is per meter cube. Whereas if we go in this Fed standards, they are based on particle size of zero point 0.5 micrometer allowed in per feet cube. Okay, that is the difference. And if you convert this to per feet cube, you will find that for class 1, it is 1 particle. Class 10, it is 10 particle. Class 100, it will be 100 particle per cubic feet. Then 1000, 10,000, 100,000, and this one is the room air. Whereas in ISO 7, 8, 9, ISO, it starts from ISO 1, which is more stringent, and the equivalent for this ISO 3 is class 1. Okay. Any doubts in this?
No, sir.
Okay. So these are classroom standards, and they are quite relevant. They come up very frequently. So I covered. So now let's come to problem 1. Which of the following operations is used to align wafers with mask in mask aligner? Linear translation and horizontal plane in the horizontal plane, rotational motion, linear translation in the vertical direction, or all of this. Like there is this wafer, if it is having some patterns, and now we want to make another pattern above it, then we will have a mask over it, okay, having some more patterns. Now we want it to align, like first pattern to second pattern. So which of the following motions will be used to do that? Any idea?
Probably option C, sir. I'm not sure.
Okay. See, linear translation motion in horizontal plane, like movement in the plane. You can say left and right movement. This is left and right movement. Okay, that's right. Then this one is top and bottom, like up and down, right? Up and down. And then is rotational, like z axis theta. Let me show you the system first, then you will be able to understand. So these are some common mask aligners. Okay, if we see it closely, actually, are these knobs visible to you? This the one I am marking.
Yes, sir.
Okay, so there are mostly two, three knobs. Okay, for X, Y moment, that is left, right. This one is for up, down. Okay, and this one is for theta, that is rotation. And why actually this three will be used here also? If you see in this aligner also, there will be this different knobs. Okay, so left, right, it is very normal to understand that if our mark, we will see this also, that if this is a mark, if this is our mark on the wafer, okay, and we have to make another mark, say like this, we have on the mask. We want both of these to be at the same place. So first thing is that we will try to move it towards it, like y direction, negative y, and then suppose it does not align, then we will again move x axis. Okay, so left right is fine, but why up down is needed is that sometimes we are not able to see this clearly. It may not be very clear when you are like when you are focusing, you want that both there is some gap between mask and the wafer. Okay, you want to see both of them clearly. Sometimes we even need to do up and down movements. Okay, so that is why both of these are needed. But what if our pattern was something like this, and we want to align it with this? Will it align just with x y? I have not drawn it well. Okay, will you be able to align it with x and y movement only, just up, down, left, right? Is it possible? It's not, right? Since
Yes, sir.
if we superimpose it above it, there will always, even if it is perfectly on top of it, there will always be some changes, like some difference. And to overcome this difference, we will have to move the angle, like we will have to rotate the mask, not mask. Mask is actually fixed. Mask we can, the wafer. Okay, we can rotate the wafer. And that's why we need to do the rotational movement also. Okay, so actually all these three should be correct. So all of this should be the right answer. Fine. Any doubts in this?
Got it.
Got it? Just put this picture. Okay. Now coming next to the alignments. Okay. Just now we have discussed. Few alignment marks are given here. So let's consider this blue one. Blue one is on the wafer and the black mark are on the mask. Okay. Select the group of mark that shows properly aligned mask and wafer. So which of these are properly aligned?
1 and 5, obviously, sir.
1 and 5,
And
yes. Yes. And
and I think we can also include 2 and 4.
no.
Okay.
Okay. Actually, I will say that this way it's very difficult to understand. Like for it looks like sometimes when you are seeing it from a side, you might feel it is aligned. Okay. So generally we don't go for such kind of mark. And if we are going for that, I will show you there are different marks, not just single, multiple marks. So it will cancel out. But this is not aligned. This is clearly not aligned, right? 3 is clearly not aligned. 2 is not
Yes.
aligned because here theta is not aligned. Theta or the angle, you see, it is at the center, just like I was talking in the previous problem. Okay, it is perfectly aligned one up above another, but it is misaligned in theta. And that is why I was saying that this kind of mark you cannot understand. Maybe like 5 may not be actually aligned, right? 5, though it looks like it is aligned exactly on the top, but may not be aligned. But seeing it, we can say for now that let's assume it is aligned. Okay, so let me show you what kind of alignment marks are there. And do you know why these alignment marks are there? Any idea why are these alignment marks?
This is to expose. I remember seeing in the video.
Hmm.
I exactly forgot the term.
Oh, not an issue. You just explain it in the way you understand. Simple, not no need of going to terms or anything. Okay. See, there when we are creating such devices, sensors, transistors, or any devices, okay, they cannot be done in one single step. Okay, and as we discussed in the previous class, also lithography is a very important step in in microfabrication. Okay, so we have to do multiple times of lithography. Suppose you made a let's say you made a ID pattern like that. We are seeing ID patterns more frequently. Okay, and then you want something to be deposited just in this area. Okay, then and the you want to create pads here. Are you able to see this structure?
Yes, sir.
Okay, so how will you ensure that this this pattern is exactly at the place we want? So what we do is that there are two type of alignment marks. One is global, when you are creating the things on larger scale, multiple similar patterns on a wafer. So in that case, you will have this complete wafer. You can have some marks here, say in the first part. Second, like this was, let me change the color. Okay, so let's say this is the first pattern. Okay, this is the first pattern. Then the second pattern we are creating like this. Okay, for ease, I will draw the whole. So in the first part, say it was just this ID pattern. Okay, then in the second mask, we are actually having this part. Okay, so it is made like that when these will align, like when these points will be on top of this plus, then this will automatically fit. We are putting it like that. Okay, then say the third part is we are creating the pads. Okay, and we have a mark like this. Okay, are you getting it now?
Yes, sir.
So there, as I said, there are two type of alignment mark. The one I am showing here is global mark. Why is it not going away? Oh, this is global mark. That if we have a silicon wafer, on that wafer there is a cut, and we have one or two marks, not single, like two, three marks, which define. Sometimes we even use local marks, like for every pattern there will be some mark with each individual pattern. Then here something else is there, maybe a heater is there. Okay, and here also some marks are there. So in this case, you can go for single device making also, but when you are in industry or commercial purpose, commercial setup, mostly global marks are the one that go. There are small local marks also, but they are generally ignored. Only global marks are taken care and they will work. But when you are making small devices, one device or two devices at once, and you don't want to use the whole mask area, you just want to use some area, then local marks are also important. Okay, so here I am showing you some examples of alignment marks. One, should I clear it? Hmm, okay, so the first one, if you see, this one is mark on the first wafer, and then there is when it is aligned second time. So you see the first part, it was just this one, these two. Second, we have this like perfectly aligned. Similarly, here we have the center marks, and then there are plus marks over it. Okay, so it look, and generally not one. We generally put more than one, three, four marks, so that you can easily align. In this case, it even it was if it was tilted, it would have looked fine. But here, since they are four, they will perfectly align. Similarly for this, C, D, and this. Now, this is an actual picture of one of my devices I have taken to show you actually how alignment. These are local alignment marks for single device. Okay, so in the first device, actually this is chrome and gold. Okay, aluminum, chrome, gold. So just a square was made. Okay, when the second level of lithography was done, here some other metal is there. So you see these small dots in between. Are these visible? This small dot kind of structure. Are they visible? Hello. Yeah. Are you able to see these dots? The central part?
Yeah, very slightly.
Okay. Yeah. Now I think you'll be able to see it.
Yes, sir.
No? So in the first stage, this just these squares are made in first stage lithography. Second stage lithography, these marks are given. Then when we are doing the third stage lithography, you see this plus mark. In fact, if you see them, it is very difficult and very faint. Like the first level and second level. First level mark was fine, but second level mark, it was not very clearly visible because a metal is deposited on top of it, on the whole surface. Okay. In this case, it was just silicon nitride. So since it was transparent, in the second case, I was able to see it. But in third case, it is not clearly visible. And here it is where we need this up and down, when we were talking in the previous question, that why we can need up and down movement. Okay, so if you see it from a bit different, slightly, uh, it is not focused. Okay, it will create problems for you. You cannot see it properly. Okay, so to do that, sometimes we might have to change the position of the wafer, like slightly bringing it near to the mask or slightly moving it away, and then we see, so that we can see both of these structures. And here you see that in order to focus on the mask, actually this structure is not very clearly focused, but we can make an idea where it is. It is not looking like a perfect plus because it is not properly focused, so that we can see both of them together. Okay, so such kind of alignments are done. for multiple levels of uh, lithography. Okay, so this is first level, second level, third level, and sometimes like many 200, 300 levels are also done when we are making some commercial devices. Clear? So going forward, so 1 and 5 looks fine, but 2, 3, and 4, they will not be considered correct. Okay, so let's move to question 3. Here, from here comes the calculation part. A layer of silicon dioxide of 1.5 micrometer is deposited on a silicon. So let's make some pictures so that it is easy to understand. So it is saying that we have a silicon wafer. On top of it, I am making in one color only. SiO2 is being deposited of 1.5 micrometer. It is patterned with a circular structure. So on top of this, there is a circular structure which is 20 micrometer using photolithography. After development, it is dipped in HF for 1 minute 30 seconds. Okay. So what does HF do to SiO2? Yes. What does HF do to SiO2?
It makes sure that the conductivity of
Hmm.
SI is not affected.
See, HF is used as a etchant. So what it does is that it etches away SiO2. So SiO2 will dissolve in HF, whereas silicon will not. Okay. But when we have something like on top of it, if we have covered it with something, that part will remain. Got it?
Yeah, okay.
Okay. So ideally, what we are trying to do is that we are trying to create a circle, like we have put SiO2, and now we are trying to create a circle, like a circle deep. So we are trying to cut out SiO2 from this part, and we just want the remaining area of the SiO2 remains. So just we want a circular hole. So what we are doing is that we are covering. Okay. Yeah. So what we are doing is that we are covering it, the complete area except for this circle area, and then we are trying to then we are putting it into a solution that will actually dissolve that. Okay. So, and after checking, this is total 1.5 micrometer, but the depth that we are getting at the end is how much? One, this depth is 1.3 micrometer only. Okay, in 1 minute 30 seconds. So, and the pattern that we wanted to be 20 micrometer have actually become 21 micrometer. And why maybe this why this may be happening? Any idea? Yes, any idea why this difference is happening? We want it to be perfect, okay, 20 micrometer, but we are getting 21 micrometer. Why this area has increased? Any idea?
No, sir.
No? Okay. So, have you learnt about isotropy and anisotropy in etching? When we are dissolving something, okay. So, ideal thing is that we want that if we are etching, it should etch vertically in one direction. Okay. But like you are from electronics and communication, right?
Yes, sir.
Okay. So when you learn about antennas, okay. So what is the expected thing is that they, in that case, it is expected that the antenna should actually transmit in all the directions perfectly. Or in some cases, it is expected that it should transmit in only one direction. But both of these situations are not possible, right? There is no such antenna which will give equal power in all the directions, or there is no such antenna which will give whole power in one direction. Okay. There also we use this same term as isotropy and anisotropy. So in chemicals also this happens that there is no perfect chemical if you are doing wet etching that will actually be able to, like if we are having structure like this SiO2 and we are covering this here. Okay. So when we are dipping it inside, what happens is that we are expecting that it should only remove this area. Okay. And the area beneath it should not be removed. But since it is a chemical, it will try to etch in both the directions. But HF is a bit isotropic, okay? Not isotropic, sorry, a bit anisotropic, okay? And so it etches this area more compared to this area. Otherwise, what will happen is that it will actually etch it like this, right? Let me put red, okay? So I like it should have happened something like this or this, okay? So it should etch in all the direction, but it is a bit anisotropic. That means it is a bit directional in sense, okay? So when we are saying isotropic, okay, isotropic means non-directional. That is the general way we think. But these chemicals are a bit anisotropic. That means they have some directional preferences. They will try to etch more vertically more and horizontally less. Okay, so they are directional, and this is what we want. But they are also not perfectly directional. They have some limit how much anisotropic they are, and that is determined by the term called anisotropy. Okay, so how much anisotropy property is there? So what is happening here is that if we see this picture here, so we wanted this kind of structure. How much was this? Yes, can you tell me what was this dimension? What we wanted?
20.
20 micrometer, right? And what we got?
21.
21 micrometer. And this whole depth is 1.5 micrometer. So we are not concerned with silicon here. Okay. So let's forget there is silicon because the maximum depth that we are getting here is 1.3. So we are still not at the end. So we are not reaching the silicon. Silicon is below this. So silicon is not our concern. So what we are actually doing is that we are depositing photoresist. At first, the whole area is covered, and then we remove that area using lithography. Okay, so we wanted this area to be removed. So we put it to a solution, and if it was like this, okay, so such a structure is formed that it started etching, but the perfect etch that should have happened is like this, but a structure like this happened. Okay, slanted way. Okay. Now, uh, do you know the formula of anisotropy? Okay, let me tell you. So, ideally, it is uh, rate of vertical edge by rate of horizontal edge. Okay. Here it is, since it is not given in terms of edge, it is about given in terms of the length and breadth. Okay. So, this one, this will be the one, it is 1 minus L upon D. Okay. L is the lateral length that we got extra, and D is the depth that it actually etched. Okay. So what will be the value of L here? Yes. What will be value of L? Any idea?
Is it 20, sir?
Why 20? See, this whole area is 20. Whole thing is 20. Okay. We are not concerned about this whole thing. We are concerned about how much anisotropy happened, how much this slant. So we are just this extra. Okay. So if this is 20 and this whole thing is 21, so how much will be this extra part, both side? Total will be
Point
1.
5.
Yeah, point 0.5, point 0.5. So this extra L will be 0.5 and depth is 1.3. So can you calculate this?
Yes, sir.
Yeah, please calculate. This will come something about 1 minus
0.61.
0.61 will be the total value. I think 0.3 something, 38,
Yeah.
3,
Yes, yes.
385 or
3846.
something. Yeah, 3846 or 4, 5. Okay. So the total anisotropy is 0.6. Okay. So 685. This is the answer, right? 615, right? So this
Yes.
is the, in short, this is the ratio how well it will uh, etch in vertical direction compared to horizontal direction. So in short, it will try if it is moving forward in like 60% of etching will happen in vertical direction. Mm, so its selectivity will be vertical direction and 60 or 61.5%. Okay, and the rest 38.5% will be in vertical direction, sorry, horizontal direction. Clear? So this ratio also it will give SV upon SH. Okay, not ratio, it will not be there. So it will be SH plus SV. Okay, so this is anisotropy, and this is a very important parameter before etching, because you might be said that okay, you take this chemical, this will etch it. Okay, but when we want very critical dimensions, this is a problem that happens. So sometimes what you have to do is that in the design itself, you have to take care of this. Instead of taking 20, if we had taken 19 micrometer, okay, so the final structure that you will get will actually be 20 micrometer. Okay, sometimes design compensations are made for these purposes. Sometimes even you some better techniques are used, because here the walls are not vertical, like reactive ion etching, that is a dry process, or deep reactive ion etching, but they are costly and time taking also. Okay, and they are not chemically selective. Here in this case, what will happen is that this chemical will etch silicon dioxide only, not other things. Okay, but when we are doing dry etching, it is less selective in the sense if it finds silicon, it will also remove that. So there are problems associated, and you have to take in mind what is your purpose and what you can do. Okay, so the answer is 0.615. Any doubts in this?
No, sir.
Okay. Now let's come to this also looks very similar. Yeah. Here it is said that silicon is there. On top of it, silicon dioxide is deposited. Okay. How much is the thickness? It is 1 micrometer. Okay. And it is dipped in HF like the previous one. Okay. Some pattern may be made. Okay. After inspection, it is the time is not given. Okay. After inspection, it shows that 100 nanometer of silicon is also etched with the silicon dioxide layer. Okay, when this whole layer was removed, along with that, maybe from the bottom, 100 nanometer is also removed. So, what is its selectivity? Like I said, uh, reactive ion etching or dry etching or deep reactive ion etching, they are not very selective, but these chemicals are selective, but they are not also perfectly selective. So when removing 1 micrometer of SiO2, it also removed 100 nanometer of silicon. Okay, which is very less compared to 1 micrometer, but it will remove. So what is the selectivity of HF to etch SiO2 in comparison to silicon? Yes, can you calculate? I think this is very easy. Seeing the question itself, you can answer. Yes,
Option D.
option D, 100 is to 1. How? It is something like efficiency. You know about efficiency, right?
Yes, sir.
So efficiency is like efficiency of removing silicon silicon dioxide with respect to removing silicon. So we can say how much silicon dioxide is removed? 1 micrometer, right? And how much silicon is removed? 100 nanometer. So this is the ratio that we want. So now calculate it. Micrometer convert it into nanometer or nanometer convert to micrometer. How much you will get?
It should be 10 is to 1. I ignore
Yes,
the units, sir. Sorry.
yeah. So 100. So if you cancel it out, it will be 10 is to 1. Okay. So 10 is to 1 will be the answer. These are very basic things. And it might look, for now, it might be looking very complex. What are these terms and all? But when you are actually trying to work over it, when you are actually trying to make these things, these small terms will actually make a lot of difference. That suppose that you don't know what is the selectivity of this a chemical, and you put it, okay, and instead of etching your required material, it etch something else also. Then what you will do? Okay, so what chemical you have to choose will also depend on that. Then you have to like suppose that is why many a times we go for very slow etchants also. because we want to protect other things. Like we don't want that silicon should be removed. We don't want that some things we have already deposited should be removed. So such compatibility issues we have to take care, and that is why these things are very important. Okay. Okay. Yeah. So I have already showed it to them that this was 1 micrometer, and here, from here 100 nanometer was removed. So we have it was 1000 upon 100, so it becomes 10 is to 1. Okay. Now this is something theoretical questions. Okay. Non-invasive detection of breast cancer can be performed by detecting the increased concentration of what a chemical in breast sample. Yes.
Ethanol?
Ethanol is this alcohol, right? So if we detect ethanol in the breath, you will say that that person is having cancer.
No, sir.
No? Then,
Acetone is also not possible. Should be
yeah,
pentane.
yeah, it is actually pentane. Okay. And there are different chemicals produced for different diseases, and these are also called as biomarkers. We talked about this earlier also, biomarkers. So, whenever a person is suffering from some disease, it is a very cumbersome task for the healthcare professionals to find out what are these biomarkers, and this bioengineering, biomedical people also do this a lot, that they try to find out what are the biomarkers, like what are the chemicals associated with the specific diseases. And so at present what is happening is that whenever there is breast cancer, uh, that area is cut out, some part of it is sent in the laboratory for diagnosis, like to check. Okay. But uh, it has also been found that whenever there is cancer, small amount of pentene is present in the breath. Okay. So if you can detect that pentene, you don't have to cut out and take out the muscle from there. Okay. Or you in some cases where we need blood and all, that also will be relaxed, right? So and to breath out, it is very easy. You don't have to do it forcefully. Okay. Or you don't have to hurt someone in taking out their breath sample. Okay. So that is why it is said non-invasive detection. So here you are not doing any harm to the patient, and you are taking out the sample, that is the breath, and you are analyzing based on it. But still there are not very perfect detectors for this, and that is why the problem still persist, and there are continuous works going on to overcome these problems. Okay. So pentane is the correct answer. Okay. For micromachining, xenon fluoride dry etching of silicon. Whenever we are talking about dry etching, it is reactive ion etching or deep reactive ion etching, in which a gas plasma is used to do the etching. Produces an anisotropic feature after etching. Is the statement true or false? Yes,
True.
true. Because xenon fluoride is used for uh, silicon's reactive ion etching. Okay. And isotropic and anisotropic I have already explained. Okay. So what is an isotropic etching? Whenever the etching happens in all the directions. Okay. And whenever it occurs in one single direction, it is anisotropic. Okay. So yeah, but in case of dry etching of silicon with xenon fluoride, actually isotropic features are made. Even though I said that mostly for anisotropic etching, we tried reactive ion and deep reactive ion. But sometimes we need fast etching and these things. So there also some specific reactive ion etchants are used and they work. So while making cantilever kind of structure, this xenon fluoride based etching is used. Okay. So have you seen this picture in the class? This image where the cantilever was made. So this etching, the etching of silicon has been done using xenon fluoride for dry etching. Okay. So this is true.
So xenon fluoride is used for isotropic feature,
Yes.
and for anisotropic it's different.
Yeah, for isotropic feature. Okay,
No,
sorry.
for anisotropic it
Yes.
is
Huh.
bromium fluoride.
Yes. But
Okay.
anisotropic we don't get when we are uh, doing wet etching. Sorry, this is actually achieved in dry etching.
Got it.
Okay, but xenon fluoride, when we are talking about this process, is dry etching. Okay, so don't confuse here with that is what I am saying that though it is dry etching process, which should generally give an anisotropic feature, but here it gives isotropic feature. Clear? Here it is
Got it.
against the like general way that though it is dry etching, but it will still give us isotropic etching. Okay. Okay. So mask aligner is used in lithography to align mask and wafer, expose the coated wafer, photoresist on wafer, develop a pattern, or coat photoresist on wafer.
Option A and B.
Option A and B. Align mask and wafer. And where do we develop a pattern and coat photoresist on wafer?
That is lithography.
So, and what is this mask aligning and exposure? Is it not part of lithography?
It is.
It is, right? So, all these are parts of the lithography. But see, when we are doing this spin coat, like when we coat it with photoresist, that is done in a process called spin coater. Okay, a, like with pipette, you put the photoresist above the wafer and then you rotate it with very high speed. That is done in the spin coater. Okay, then it is what is the next step once photoresist coating is done? Then yes, can you tell me anyone? What is the next step in lithography? All the steps of lithography. So if when we are doing the first is PR coating, then uh, so the next one that is done is soft bake. Okay, then we go for mask alignment plus exposure, and this is done in the this is one of the most important part of the lithography and sometimes referred to as the main lithography here. Okay, and this is done in this system, that is mask aligner. Okay, and then we develop, and then we do hard bake. Okay, so development, this will be done on wet bench, that is dipping inside a chemical and all, and hard bake we will do. So in so these two will be the correct answers. Okay, but here these things are done on a this is done in a wet bench, and this is done in a spin coater. Okay, any doubts?
No, sir.
Okay, yes. Now this is something which we discussed at the very beginning of this class. It is related to that. Why split field microscopy is used in mask aligner? When we are aligning the mask, why split field? That is two uh, two microscopes at once are used. When you see, generally what we do is that we have one lens and we see the area. But in case of mask aligner, there are two microscopic systems seeing at two different places of the mask or the wafer at the same time. So when you see on the left hand side, you will see the left microscope, right hand side, right microscope, two parts divided into two parts. Why? Is it because split microscopy is easier to install and does not require optimization, or it helps in viewing the alignment mark from both the microscope at same time, or dimension of electromic alignment marks are in micrometer, microscope are required to observe those while aligning, or is it because it gives better resolution? Yes. What may be the reason for using split field microscopy?
Option C.
C. Okay. Yes, this is fine. Any other option?
And it also helps to see from both the
Yes.
align
So,
faster.
yes, because as we discussed in the starting, that generally there are multiple marks and they are kept at two different places because we want that the whole wafer is perfectly aligned. Okay, like I showed you global marks. Okay, so sometimes we may have these marks at two very uh, far away places, and you cannot keep moving your microscope from here to there, and in this process it might happen that you aligned at this point and that point actually the alignment got disturbed. Okay, it looks like it is perfectly aligned here, but on the other hand there is some jet movement that actually destroyed it. So it will take more time. So to overcome that problem, there are two microscopes working at the same time. So you put them at two different places, uh, one at one alignment mark, the other at another alignment mark, and then you are able to align them. Like if the alignment at right hand side is fine and the left hand side is fine, then you go ahead. Otherwise, if it is if you are adjusting at right and it is disturbing at left, you take care. No, no, we don't have to do. We have to do the other way. Okay. And the obvious thing is that since these are in micrometers, microscopes are required. So they must be done, and there is no difference of resolution. It is even if you are seeing there is an option to see single also, like use one single microscope at a time. You can go for that also. There is no difference in resolution, and it is not easy to install. It is very tough to install actually. It is a very cumbersome way where two microscopes are connected in one single eyepiece. Okay, so it is a bit difficult. So there are actually two objective systems and one eyepiece, like we have in microscope. Okay, and if in the wafer we have two marks at different places, we will be able to see both of them at the same time and align. So we don't have to worry about uh, moving from left to right. And there is one more reason to do that, because the microscopes are not able to move for very large area. There is uh, limited movement for one microscope. So either you will have to shift from left to right and then do this. So instead of that, both of them has been made together. Okay, so these are the right answer. Any questions in this? Uh, this is a very important question that comes very frequently. That lithography process has three modes of exposure. Okay, depending on the distance between the mask and the wafer. These are contact mode, proximity mode, and projection mode. Which of the following is false regarding the exposure? Okay, so before going to question, let's see what are the three different modes. Are you clear with these three different modes of exposure? Yes, anyone can answer. So let's see. There are three common modes of exposure. One is contact, the other one is proximity, third one is projection. In contact, it is the mask and the wafer with PR coated over it are close together, like just they touch each other and then we expose. The second one is proximity, and this is one of the most common type. Okay, in this case, what happens is that the mask and wafer, they are very close but not touching each other. Still, there is some gap. And the third one is projection, in which case, after mask, there is some lens to uh, make to project the pattern over the wafer. Okay, so based on this, uh, which of these are false? Effect of diffraction of light is minimum in case of contact lithography. In contact mode, the mask can be contaminated by photoresist during alignment. Contact mode cannot support batch production. Contact mode of exposure can give a better exposure, better resolution than other two modes. Yes. Yes. Anyone? I think today, uh, okay, only two persons have joined. Yes. Anyone?
Option C.
Option C. Contact mode cannot support batch production. Okay. Mm, A effect of diffraction of light is minimum for contact lithography. Is it true? And why is it true if it is? Yes. Not an issue. Even if you are wrong, it is fine. It is something that we are trying to learn. Okay. It's, anyone? See the when we are talking about contact lithography. So you see here between mask and this wafer, actually there is no gap. So there is no way there can be some diffraction. And when we are putting the mask, actually the pattern is not on the top, the pattern is at the bottom. So in a sense, the pattern is touching the PR. So there can be no diffraction at all. Okay, so this is true. In contact mode, the mask can be contaminated by photoresist during alignment. So it is very clear that since it is touching, and photoresist is a sticky substance, liquid kind of substance, which has just been bought after, like you just coated it and did a soft bake, but still it is somewhat sticky and it can contaminate the mask. And that is a reason that many contact mode is not preferred by most of the people, because that there the mask has to be cleaned, and in that process the mask wears out very easily. Okay, so it is having a shorter lifespan. This third is contact mode cannot support batch production. Batch production means we are trying to expose multiple, maybe 10, 100,000 of wafers at once. This is uh, correct. Is this correct?
No.
No. Why? In contact mode, uh, batch production is a bit difficult because here the photoresist sticks and you have to clean it. Okay, so that is true actually. This is okay, and it says that contact mode of exposure can give a better resolution than the next two modes. This looks true, but there is a catch. Certainly, this will have a better resolution compared to proximity, since there the diffraction will happen. But here you see in the case of projection, we can scale up or scale down using a objective lens in between. Okay, so this lens actually takes care of the diffraction, as well as you can go for lower resolution than the mask. If mask is having some resolution, we can narrow it down using lens and we can go for lower resolution. And that is why this will projection has the best resolution in all three, not the contact. Clear?
Okay.
Like getting it, or is it unclear why this is happening?
No, got it, sir.
Got it? Right. Okay. So the incorrect one is that it will have the best resolution. This is not also perfectly close, perfectly correct, but since this is a problem that is faced in batch production, okay, so we can say that this is somewhat correct, because one, two, three exposures you can go, but after that it will get contaminated. Even when we are doing a proximity exposure, many a times it happens that it comes so close that it gets contaminated, and then you have to clean it. Okay, so that is a reason that nowadays projection lithography is more preferred, but that again is costlier and requires uh, more skill, because there, since a central lens is there, there you have to take care of other things also, that like there can be some other complexities as well. Okay, so let's come to problem 10. An array of cantilever is fabricated and characterized. Okay, cantilevers is when we have something hanging, a hanging structure kind of thing. Okay, in the wafer, like we have this silicon wafer, and here there is a cantilever. Yes, Shanti, you have a question?
Good evening, sir.
Yeah, good
Sir,
evening.
among three lithographics, which one is printing a small feature size of particle?
Yeah, this one. The best one for small is projection, because here, if we have a mask of say this size with some patterns here, okay. So using the lens system at below it, this one, we can actually make it to a lower resolution. Okay, that is why projection is having the best resolution. Like we can go for the lowest feature size. Clear?
Thank you, sir.
Yeah. So now is an array of cantilever is fabricated and characterized. It is found, array means multiple, we are making multiple cantilevers. Okay. It is found that it cannot meet the expected efficiency. So what we wanted, we are not getting. What may be the reason behind it? Cantilevers may be destroyed during etching. Cantilever may be buckled up due to stress gradient of oxide and nitride layers. So oxide layer is there, then nitride layer is put on the top. So it may have buckled up. May not be released properly before removal of sacrificial layer. So the layer below it, it has been removed, but the cantilever was not properly released, or all of this. Yes, you can unmute and speak up. That's fine. Yes,
D, all of these, sir.
all of this, because all of this are actually some steps that can be causing problem. So we have to inspect after every step, and we check that inspection is done using SEM or optical optical microscope. But when we have very small structure, we go for SEM or FESEM. Okay, so it might be that this whole structure was actually not formed at all, or it may be that has moved a bit up due to some stress building here above it, or it may not be properly released, that it is not vibrating or not moving at all. Okay, so all of this. Now let's come back to a similar question that we have done. The anisotropy for the eventual profile after this process is carried out is equal to what? So in this case, very similar to the previous one question, the shape from 5 micrometer has increased to 6 micrometer, and the depth that we have obtained is 2 micrometer. Okay, so what is the anisotropy for this? Anyone? Yes, we have discussed this, right? What is the formula for anisotropy?
Option D.
Option B. Okay, but and tell me what is the formula for anisotropy? A equals to, what is the formula?
1 minus L by D.
L by D. So what will be L here?
1.
Here you are mistaken. See here. This one is divided in both the parts. Okay. So when we are talking about anisotropy, we take only one part. Okay. This extra one is half here and half here, right? Now what will be the anisotropy? 0.5 upon 2, right? 1 minus 0.25. So that is 0.75, right? So we have to take care that whenever such questions are given, actually the growth is on both the sides, and not just both the sides. If you see from the top, it is from all the sides. Okay. So when we are seeing in the figures, it looks like just 1 micrometer growth. But if you check the difference in case of area, it will be something like um, 6 minus 5. Okay. Pi 6 square minus 5 square. This is the area, right? This is the difference in area. So it will be 5 into 36 minus 25, that is 9. So 9 pi growth of area will happen. Like, and actual area we expected was 25 pi. So if you compare this, this is very large, 9 upon 25. Okay. So though it looks like very small change when we see the side view, but the real growth of area that happens for this small 1 micrometer growth, half from both the side, the actual growth is too much. The total area, the extra area that forms is too much, and that is why anisotropy is a very important factor. Okay, and here it will be 0.75, not 0.25. Clear? Now let's come to problem 12. Okay, here the sorry. Here the anisotropy is already given, that is 0.5. Okay, a process P1 is carried out. Sorry. Here time is not given. It is just said a process is carried out and the final schematic is shown in the figure. The thickness of SiO2 film is in microns. Okay, like you have to find out thickness of SiO2. This one in microns. How can we proceed for this? Yeah, this thickness we have to find out. So in this case, what is happening is that it etches this whole thing as well as it etches the silicon layer a bit. And this at the bottom where silicon and uh, yeah, the silicon and SiO2 meet, this gap is given as 0.25 micrometer. Okay, so and anisotropy A is already given as 0.5. Okay, 0.5, and we know the formula of A equals to 1 minus L upon D. Okay, so what will be the value of L here? A is already given, so it is 0.5 equals to 1 minus, and D we have to find out. This is the D, right? So what is the value of L here? In this case, what you said, Versa, that 1 micrometer growth. Okay, so in this case, the total growth is 2 micrometer, 1. Okay, so here we will take 1 micrometer. Is it correct? We will take 1 micrometer here. Yes,
Yes.
sure. Now, if I draw a small line here, Now this distance is 0.25, right? So now what is the value? It should be this till here. Hmm? Yes. Now what will be L? Total is 1 micrometer. But if you see the profile till the end, you will see that what has happened is that it was like this till it reached this lower point. But after that, it also started etching silicon for some time. Whatever time might have been there, in that time, it etched this part, right? It went upward. So we are not interested in this whole part. We are just interested in this part, the end, the L that was there. So to find out, we see that here it has etched 0.25 here. So actually we will remove that extra part. So it will be 1 minus 0.25. Getting it? Now try to solve this for D. D is the depth that we want to find. Fine. So what will be the value? So we can say 0.75 micrometer upon D equals to 1 minus 0.5, that is 0.5, or D equals to 0.75 upon 0.5 micrometer. So what is the value? 1.7, 1.5, something like that. 1.5 is enough. Is it correct? Can you do the calculation? Yes, anyone? Yeah, Prashanti, can you try?
That's right, sir.
It's right, right? So,
Sir.
yeah. So the correct. So we have to take care that when we are talking about this anisotropy, it depends on the material. So anisotropy for silicon is given. Silicon dioxide is given. For silicon, it will be different. And in this case, remember we have talked about selectivity also. Okay. So when we see it, it looks like okay, this is very small. But since at, uh, in this process, it must be that the chemical used is selective towards SiO2. That is why a very small amount of silicon has only been removed. Okay, so if we want, we can even find the selectivity. What is the selectivity in this case? Can you try to find out what is the selectivity in this case with SiO2 versus silicon? Yes, we already know the anisotropy. Okay, so it's zero point 0.5. Now, if we say this distance, okay, if we see this distance, so this distance is 0.25. So this is L 1 minus 0.25 and D. So what if this portion was also silicon dioxide? So how much silicon dioxide would have been etched in this time? So if we solve this, we will find 0.25 upon D equals to 0.25, which implies D equals to 1. 0.25, uh, 0.5, okay, sir, not 1. D equals to 0.5, 0.25 upon 0.5, yeah, 0. So half micrometer. So in place of half micrometer silicon dioxide, only 0.1 micrometer of silicon has been etched. So selectivity will be 0.5, 1.1 is 5:1. This is the selectivity in this case. Clear? So in such questions, we can find out uh, anisotropy is already given, so we can find the selectivity. And if these dimensions were given, like this whole thing, we could have even find out what is the anisotropy in case of silicon. Okay. Any questions in this? So 1.5 is the correct answer. Oh. Now a square mask with dimension 10 micrometer is aligned such that one of its sides is along the wafer flat of 100 wafer. Okay, flat of okay. After KOH H is carried out, the area of the square pit at the top will be how much? So we have this, okay, and remember when we are talking about KOH, it has a very unique property that it etches 100 plane but stops at 111 plane. In fact, there should be brackets. Okay, okay. So what will be the area? And this area is 10 micrometer. Okay, 10 by 10. Okay. So what will be the final area of the pit? Yes, yes, you can ask. Uh, you are asking something, Prashanti?
No, sir.
Yes. Any answers? Yes, please. Yes, yes. Uh, can you try? Anyone? Okay. So let me. I think there's no. Let me put one blank sheet here. Just okay. Okay. So we are talking about this is a wafer. Very bad in drawing. Okay. Let's just create like this. Mm, do it the way we were doing. So suppose on this wafer, uh, I am not able to make it clear. So this is 100 cut. Okay, this should be round. Okay, I am not able to draw it. So this is the primary cut. So this is 100. Okay, so there is a structure like this of 10 micrometer dimension. Okay. Now, since it is being etched by KOH, what will happen is that it will etch the uh, it will etch the 100 plane, and it will stop at 111 plane. And the angle between 100 and 111, what is the angle? Anyone? Sorry, not 111, 110, right? 110 plane. What is the angle? Anyone? This 111, no? 100, 11. What is the angle? Anyone? Okay, first let me draw, then you will be able to. So when etching, it will make a structure like this because it will stop at that point like this. And now we want to find the area of this. For that, we need to find the size of this square. Okay, so the area between 100 and 110 is 45 degree, and since that is the area, that is the angle, what will be the side? The side will be cos of that, so it will be cos 45 degree equals to our uh, value 10. So not 10, so since it is half. Yeah, so if we make a triangle here, okay, so this is half 5. Okay, now we want to find this half. Let's do it like that. And since the angle here is 45 degree, okay, so it will be 5 upon x, hypotenuse, base upon hypotenuse. So it will be, let's say it as x. And then if we show it, what is cos 45 degree? Yes, anyone? Anyone remembers what is cos 45 degree? Yes, Versa, you are saying something.
One by root.
1 by root 2. Okay, and then 5 on x. So if we solve this, it will be x equals to 5 root 2, right? So what is the final side? It is 2 times this, 2x, right? So it is 10 root 2. Okay, so what is the size of this square now? What is the area of this area of a square? Side square, area equals to side square, right? So on solving this, what we will get? Area will be 10 root 2 squared equals to 10 square into 2 equals to 200. Is it correct? So what will be the correct answer?
D.
D, 200 mega. Are you able to get this, or there is some confusion in this?
Got it, sir.
Got it? Okay. And why the angle is 45 degrees? Anyone can try. Why the angle is 45 degrees between 100 and 1110? Yes. How, not why, let's say how the angle is 45 degrees.
In 100, it's 180 degree.
Mhm. 180 degree. Okay. Let's make the unit cell first. Okay. So this is the unit cell. So this is one, this is one, this is one. Okay. So which one will be 100 plane? Uh, let's make 3 points, then we will draw. So 100. Let's say this is X, this is Y, this is Z. Okay. So what will be the first point? 100. So on X, what will be the value? Here it will cut here. Let's take one different color, right? Hmm. So 1 point will be here. The other 2 points, 0 and 0. For Y, 0 means invert of 0, that is infinity. Okay, so Y it will go on infinity, Z also it will go on infinity. So the plane will be something like this, right? This is the 100 plane. Is it correct? And what about 110 plane? Let's take one another color. Mm. Is it correct, Barsa? Hello? I can hear some noise from you, but not
Yes, sir.
yours.
Yes.
Okay.
Am I audible, sir?
Yeah, now you are audible. Okay. What about 110? So on x-axis, it will be same. On y-axis, it will be here. And on z-axis, it will be infinity. So it will be something like this. Okay. Now, if you see it, what is the angle? If you calculate this, what is the angle here between them? What is this angle at down?
That's
Is this,
90 degree.
yeah, the whole angle is 90 degrees, certainly, since they are perpendicular. Between them, the angle will be 45. How? Because this is one, this is one. So the tan 45 degrees one, uh, right? So 1 upon 1 is equal to tan theta. So if we solve it, we will find that tan theta equals to 1 implies, yeah, which implies theta is equal to 45 degrees. Okay. So the angle between this, if this is 45 degrees, so certainly 90 minus 45 also gives us 45. So the angle between 100 and 110 plane is 45 degrees. And KOH is plane selective. Like when we are talking about these things, anisotropy and these things, there are many different ways of anisotropy. Some of chemicals are actually uh, more fond towards one material and not selective towards other. Some are selective towards some certain planes. Like some, it will be able to etch in one direction but not in another direction. So such anisotropy exists. For KOH, it is about 100, and in general, 100 is the easiest to etch, uh, followed by 111, and the toughest one is 110. Okay, and in case of growth, thermal oxidation and all that we will cover later on. In that case, there is a difference between it. The opposite is 111 plane becomes the most favored one, and 11 110 is less, and 100 is the least favored one. So oxide growth and all that we will cover. So for this one, you are able to get how it is 200 micrometer. A bit of mathematical calculations will be involved. Okay,
Yes,
so
yes.
we have to see how it is happening. So when we are seeing from the top, till PR is there, it will look like a square. When you remove the PR, you will find that the sides have grown a bit and the whole structure has shifted a bit like this. Okay, so finally we will get a structure like this. Now come to next question. During lithography process, after hard bake, the photoresist is not stripping well using acetone and IPA. Which of the following system can help in stripping the resist? After the whole lithography process has been done, uh, like spin coating, soft bake, soft bake, exposure, then hard bake, then developing. Then we have even uh, done this. We have removed the structure below it. Now we want to remove the pattern that has been hard baked. Okay, now we want to remove it. So that is done using putting it in acetone. But sometimes it does not re get removed. So what of the following can be used? Shaker incubator, sonicator, strip plate, or stirrer with hot plate. Yes, yes, Versa.
Should we C or D?
C or B. Yes. See, when we are doing this process, we have also to take care that it does not destroy the existing structures. Okay, we can go with any of this, and we will be able to get out the like ease out the stripping. But then what will happen is that in all the processes, some damage can happen to our existing structure. So the best way is to go by sonicator, because it it is just an ultrasonic wave in a liquid that will try to shake up the molecules instead of shaking the whole structure. Okay, like in all other cases, shaker incubator or strip plate or stirrer with hot plate, the whole thing is moving, and that can actually damage our existing structures that we have made with so much of difficulty. Okay, so to take care of that, the best option is to sonicate it, like put it in a sonicator, so ultrasonic waves will be sent through it. So there are small sonicators. In fact, when we are doing the degreasing process, you must whenever this wafer, everything we are talking about, actually before every process, some cleaning has to be done to take care that no contamination is there. Some standard cleaning processes are there, but apart from that, just putting it into acetone and sonicating it, that is one of the simplest process to clean the things. Okay, and there also this thing happens that this ultrasonic waves, they just shake out the things and this will easily come out. Okay, so we need to shake, that is fine, but we must also take care that we are not destroying the structures that we have made. Okay, if we are putting it to some harsh processes, like uh, it will have some collisions with some other things, it will destroy our purpose. Okay, so that is why we go for sonicator. Fine. Now let's come to next, that is buffered HF. Okay, buffered HF, hydrofluoric acid, also known as BOE, is used to etch out silicon dioxide. Okay, we have seen in many questions that it was with. Which kind of etching is this? Isotropic and dry etching, isotropic and wet etching, anisotropic and dry etching, or anisotropic and wet etching? Yes. Is it, first tell me, is it isotropic or anisotropic?
Isotropic.
Isotropic, that means it happens in all the directions. Remember, we found out something called anisotropy. Okay, it is not isotropic, or and it is neither anisotropic perfectly, but it have anisotropy. How? Because something like 0.75 or 0.25, anything. So it is isotropic in nature, but not perfectly. If it has anisotropy equals to 1, then it would have been perfectly isotropic. Okay? Sorry, not isotropic. Perfectly anisotropic. But it has isotropy. Uh, why am It has anisotropy, but not a perfect anisotropy. And here there is no talk of perfect. Okay? But in case of isotropic, when we are talking about isotropic, that means it is totally isotropic. Okay? Which is not isotropic, means equally in all the directions. Okay? No process ideally is perfectly isotropic or anisotropic, but if we are able to get isotropic general ones, like where you are able etching in all the directions, they are isotropic. We want more anisotropy, and that is why these chemicals are used. And this is wet for sure. Okay, and we can say this is anisotropic, not isotropic. Isotropic, in that case, it would have edged in all the directions equally. It is not doing that in equal direction. When anisotropy is equals to zero, not zero. I'm saying it wrong. Vertical is equal to, okay, sorry. This should be 0 and this should be 1. Yes. When anisotropy is 0, then it becomes perfectly perfectly anisotropic. And when anisotropy is 1, it will be perfectly isotropic. Okay? Because vertical upon horizontal will be equal. That means it is isotropic. Okay? Any confusion till
Okay.
here? Okay? So, I think it's a bit confusing topic every time. In fact, I also get confused with I, like the terms isotropic and anisotropic. Okay? So, any other questions till here?
No, sir.
Okay. So, that's all for today. See you in the next class.
Thank you, sir.
Thank you.